A classic static equilibrium problem is a ladder against a wall. So you see over here on the right hand side, I've drawn a red wall. I've got a ladder leaning against it. And so because this is an extended object, we have to consider the fact that it can rotate. And so with static equilibrium, that both the net force and the net torque are equal to 0. So with net force equal to 0, it means that there is no change in the velocity of the ladder. And with net torque, there is no change in the rotational rate of the ladder. So if we think about what's happening with the ladder, we know that the weight of the ladder acts toward the center of the earth. We also know that because the bottom of the ladder is sitting on a surface, that there's a normal force with the floor. There's another surface here, that's the wall. So there is a normal force perpendicular to the wall. And then we've got some friction that is acting along the floor here. And we'll say force due to friction for the floor. That's static friction. There also then is some friction that's keeping the ladder from sliding down the wall. So we've got those forces essentially that are acting. And so the net force equals 0. So that tells us that the weight of the ladder is supported by the floor, normal force, and this friction with the wall. So we can actually write that out. And we would say mg is equal to friction with the wall plus normal with the floor. Now remember, friction with the wall is the coefficient of friction between the wall and the ladder. The normal force of the wall, that is by definition, so plus the normal force of the floor. So just doing a little bit of substitution so we can kind of see what things that we can use. Then we have in the horizontal direction, we have that this force due to friction here and the normal force of the wall have to be equal to one another. So we can write that the force due to friction with the floor is equal to the normal force that the wall supplies. And keep in mind that the friction with the floor is the coefficient of friction with the floor, normal force of the floor. So that's going to allow us to do some substitution in this case. Now we're going to introduce the idea of torque. And so with a net torque being applied, our angular acceleration is 0 here, so there is no net torque. That means the twisting action of each one of these forces is balanced. And so the forces that are causing clockwise rotation and the forces that would be causing counterclockwise rotation are equal to one another. In order then to solve for net torque, we need to pick an axis. So the first thing we'll do is assign an axis. We can pick any one we want to. A good one to pick here is this point here with the floor. The nice thing about that is then there are two forces for which the lever arm is 0, and so we only have to consider the torque for the other three forces. And so if I'm writing the net torque, that is the torque from the friction with the wall, the torque from the normal with the wall, and the torque from the weight. All right. So if you recall, torque is R cross F. And so we're going to be looking for the R value for each one of these and the force. Okay, so let's look at one of the cross products for the torque here. We set the axis down here at the bottom. And so we had 3 different forces besides the one here, the 2 that were acting at the bottom. And so I'm going to take one of those and go ahead and just think about it. So here is the normal with the wall. And then I want to think about the R vector for that. That is from the axis out to the point where the force acts. So R for this wall looks like that. So if I'm going to write that, I see that the R vector has both an X and a Y component. I've got R wall Y and R wall X. So torque is a cross product. Remember, order is important, so this is going to be R cross F. And so I have R of the wall cross the normal with the wall, and that yields this matrix. And so now I can solve. And so cross product, there are no remaining terms in the I hat direction. And then we're going to look at the J hat direction. Same thing, when I look at J hat, I get no remaining terms in the J hat direction. But with the K hat, I get one term, and that is the negative. So the X component times 0, and then minus normal to the wall, but that's a negative component, times the Y component, and that's all in the K hat direction. So that's positive, normal to the wall, radial vector, but that is opposite to phi, so I can say sine phi in the K hat direction. So K hat, that is into or out of the screen. This is positive, so that means it's pointing toward me or out of the screen. And so that lets me know that this vector would cause a counterclockwise torque because it's positive. And if I were holding down here at the axis and applying a force in the direction of the normal force, I would get a counterclockwise rotation. So this is the torque for that vector. And we can do the same thing with the other vectors that we have there. So we had the friction. So we had friction with the wall. And if we look at it, we see that we end up with a Y component only. And so when we do the radius, same radial vector, cross this, we're going to end up with And so when we're looking at the I, j, and k components, we end up with a k component. And so that is RWX FW. That is positive, and it is k hat. So that's another counterclockwise torque, and sure enough, that's what it looks like would happen there. So I'm not surprised that this is positive. If I look at this component here, then I can write this as RWX cosine, sorry, not X, RW cosine of phi times the friction with the wall in the k hat direction. All right, so the last of our three forces, we've got our axis down here at the bottom. The other force that we had acting here was the weight. And so we want to find the cross product. So here is R of the weight, and I want to find the cross product. And so when I'm looking for the torque, all right, so again, we've got that same angle we labeled on the last picture. We called it phi, so we'll go ahead and label that here. Notice that this R for the weight is half the length of R for the entire length of the ladder. So I'm going to write that up here. The magnitude of this is equal to the magnitude of the wall over 2, just in case we need that substitution later. I want to show that here on this picture. So if I'm looking, I've got both an X and a Y component for R. So when I find this torque, I've got RMGX, RMGY. Both of those, this one is right and up, and there is no component in the k hat direction. MG is all pointed in the j hat direction negative. And so when I go to find this, there's no I hat component. There's no j hat component, but there is a k hat component. And so when I'm looking, I see RMGX times negative mg, and then that's in the k hat direction. And so RMGX is RMG cosine of phi. I'm going to put the negative sign out front. MG k hat. So that tells me that this is trying to cause a clockwise rotation. Oops, not counter. Clockwise rotation. And so that's where I get this negative sign. And so my net torque then is the sum of all of those. So I had R of the wall sine phi times the normal of the wall plus R of the wall cosine phi force due to friction of the wall. And now I have RMG cosine phi times mg. All of these are in the k-hat direction. So now I can sum these and I will have the net torque. Again, I've got the substitution, so I can change so all of those are measured the same. So I just need to know the length and I need to know the angle, and if I knew just a couple of other things, I'd be able to go ahead and solve this with numbers. But I have the net torque and the net force, and that gets me started on any problem where I'm thinking about an object that is in static equilibrium.